How does a dye-sensitized solar cell work? In this tutorial, I will dive into the mechanics and the structure of this solar cell technology. And first off, I'm going to use the abbreviation DSSC for dye-sensitized solar cell. And the type of DSSC we're going to talk about is this structure you see right here, where you have two glass slides like this, and then a bunch of functional materials in between that are sandwiched in between. So you see an image of what they can look like, where you have the two glass slides, and in between you have all these sandwiched materials. And in this tutorial I will go into the details of how these work and how they end up being a solar cell. So DSSCs can be used for different applications. The glass type DSSC can, for example, be used for glass facades, like in this building in Switzerland. But let's dive into how the actual solar cell works. Starting off, we're always going to need a light source, such as the sun. But DSSC can also use indoor lighting as the light source. And light produces photons, a little package of light energy. And that's where everything starts. In a DSSC, we have a dye molecule, which I represent like this. Dye molecule. And that dye molecule has the ability to absorb the energy of light. So when a photon comes in, it can excite the molecule. What that means is that the electron is free to move around. It is no longer completely bound to the state where it was before. And what it leaves behind then is a little pocket, a hole where the electron used to be. So we have an electron and a hole. To be able to utilize this energy now stored in the excited electron, we need to close the loop. So to be able to get an electric current flowing, we need to close the loop so the electron goes from the dye molecule around into whatever load we're going to use and then come back. How is that done? Well, first off, the dye molecule sits connected to a semiconducting material. I'm going to draw it like this. So this is a semiconductor. But it's not just a flat layer, it's actually a nanoparticle network. Why would you use a nanoparticle network? Well, the thing is with nanoparticle is that they're so small, so even though you make a quite thin layer like this, you will have a huge surface area. And this is a really important feature, because you want as many dye molecule to sit on these surfaces as possible. I'm just going to draw a few here, but in reality, pretty much all the surfaces are covered with these little dye molecules. Okay, so once the electron is excited, it is able to jump over thanks to this anchor, to the semiconducting material. In the semiconductor, it can flow around, and it will eventually end up on the working electrode. The working electrode, which I'm going to draw like this. So, working electrode. The working electrode is usually just a piece of glass, but the glass is layered with a thin transparent conductive oxide. transparent conductive oxide. This is abbreviated TCO. And a common example of this is indium tin oxide, one of the common transparent conductive oxides. What the transparent conductive oxide does is it provides a route for the electrons. So the electrons can now go with less resistance through this layer until it reaches a contact that we make. So we can solder on like a copper wire or something where the electrons can flow easily. And then we connect this wire to some kind of load. Maybe this is a light bulb or a pump or a battery or whatever you like it to be. And then the electrons flow to the other side of the solar cell. Obviously, this is not drawn to scale. The solar cell in total will just be like a centimeter or something. Actually, less than a centimeter. So, on the other side, we have what's called the counter electrode. Counter electrode. Which also has some kind of conducting layer. It doesn't necessarily need to be transparent because it's only on the working electrode side where we need the photons to pass through. Here we can have some other connector like a metal, for example. Okay, so now we have the electron over here, but it needs to go to the dye molecule to be able to close the loop. And to do that, we are going to use an electrolyte. Electrolyte. And in most cases, it's a liquid electrolyte. Doesn't necessarily have to be, but it's the most common choice. So electrolyte is basically a liquid that contains ions that are able to pick up electrons and drop them off at the dye. So one of the most common electrolyte is the triiodide iodide electrolyte. So we have a triiodide ion that looks like this. It's negatively charged, and it is able to pick up an electron, and it actually picks up then 2 electrons to become 3 species of iodide ions. So where we had 1 negative, we now have 2 negative. So they should to make it correct, we should say that there's 2 electrons getting added here. This could happen on its own, of course, but it happens very slowly, and to speed that up, we usually add a catalyst. So we cover the counter electrode with some type of material that is called a catalyst. Catalyst. A very common choice is platinum. Platinum metal is a noble metal, so it doesn't corrode, and it also has really good catalytic properties. So it helps the electron to go over to the electrolyte species. From here, the electrolyte with the electrons flow around at random, but once they end up next to a dye molecule, they're able to take that electron and pass it over to the dye, which means it fills the hole, and the dye is now ready to absorb another photon. After the dye has, or after the electrolyte has dropped off its electron, it once again becomes the triiodide ion, which then diffuses back and picks up new electrons and passes them over to the dye molecules. So to summarize, we now have photons coming in, which excites electrons. Those electrons are able to go into a semiconductor network of nanoparticles and diffuse around in that network to the counter electrode, where they are conducted through a transparent conductive oxide to a wiring that goes through our load back to the counter electrode. At the counter electrode, there's a catalyst, which enables the electron to pass over to a liquid electrolyte. And in that electrolyte, it travels all the way to the dye molecule where it's replenished. And that closes the loop for the dye-sensitized solar cells.